Today we are going to talk about elements, atoms, symbols, basically the foundational terminology and foundational concepts of chemistry. And we're going to start with elements. So what are elements? Elements are substances which are pure substances, so they're not compounds. And elements build up all other things, all other compounds. Elements cannot be broken down chemically into simpler substances, and many of them are listed in the book that you're using for this class. Names of the elements come from different sources, from planets to colors to famous people. Some examples are shown here. Titanium, that's used in the airplane building, comes from Greek mythology. Iodine and chlorine come from Greek words for the colors for the elements. Chlorine gas is indeed greenish yellow and iodine is violet. Curium is named after Marie and Pierre Curie. Each element is represented by a chemical symbol, which always consists of either one or two letters. There's not really a common rule. You will memorize the symbols for the elements as you move along. So far, you need to know the symbols for the elements of the first, second, and third periods. It's going to get more clear as we move through the lecture. Memorize the symbols for bromine, iodine, potassium, calcium, and all the noble gases. And iron, cobalt, nickel, molybdenum, copper, zinc, chromium, and manganese. All of this is listed in the study guide, so just focus on that study guide. Those are the symbols that I can ask you about. You have to know them for the exam. So here are some, names and symbols, some common elements. Again, focus on the study guide. Now here are some examples. For instance, silver, its symbol is not Si, it's Ag from Latin argentum, which means silver. And gold, for instance, its symbol Au comes from the Latin word aurum for the gold. Now, one of the most important elements, if not the most important element in living creatures, is carbon. Carbon has a symbol C, and interestingly, carbon can be arranged in different ways, thus producing different substances. For instance, if carbon is arranged into the layers, it will form graphite. If it's arranged into very interconnected 3D structure, it will form basically an opposite, physical opposite of graphite, diamond, the shiny, extremely solid material. Carbon can be formed into nanotubules, into fullerenes, into graphenes. So there are multiple ways for carbon to arrange its atoms, forming different substances with very, very different physical properties. So elements are organized in the periodic table, which organizes 118 known elements. You can see that some of them don't even have a name. And the principle of organization for elements is that they are placed in the order of increasing atomic mass and increasing atomic number. Most importantly, increasing atomic number. So this number 1, 2, 3, 4, 5, and so on, they represent atomic number. And jumping a little bit ahead, we can say that atomic number corresponds to the number of positively charged nucleons, positively charged protons in the nucleus of each element. So elements are arranged more or less into columns and periods according to their properties. Columns contain groups, okay, and they contain elements with similar properties. Horizontal rows are called periods, and they are numbered as periods 1 through 7 from top to the bottom of the table. Group numbers, on the other hand, are written on top of each group, and there are two ways to number the groups. One, more classical way, I would say, uses the letter A for representative elements that are located in the groups 1A through 8A. And that method uses the letter B for so-called transition elements that are located in the groups 3B to 12B. An alternative way to name the groups is to assign simply the numbers from 1 to 18 to all of the groups from left to right. In this case, first and second groups contain only representative elements, as well as 6th, 7th, and 8th. 16th, 17th, and 18th group. All others contain transition elements. So in this text, we're going to show both systems for numbering the groups. So here you can see group 2A and the period 4, and it explains what the group and the period. So this is a group, this is a group, this is a period. So here are representative elements. The first group of representative elements, 1A, is commonly named alkali metals. Group 2A is named alkaline earth metals. The group 7A is named halogens, and the group 8A is named noble gases. Groups 3A through 6A actually do not have common names. So alkali metals, most metallic metals of all, include elements like lithium, sodium, potassium, rubidium, and cesium. All of them are extremely reactive. Sodium can react with water, resulting in explosion. Group 7A, on the other hand, the halogens, they include extremely toxic and also highly reactive elements such as fluorine, chlorine, bromine, iodine, and astatine. All elements can be separated into metals that are extremely to the left, nonmetals that are extremely to the right, and metalloids that are located along the zigzag line between metals and nonmetals. You can see here the zigzag line. So the green elements here will be metalloids. Elements highlighted in yellow are nonmetals, and all elements highlighted in blue belong to metals. Metals are usually shiny and ductile and very good conductors for electricity and heat. Nonmetals are dull and brittle. Usually they do not conduct electricity or heat well, and they actually work as good insulators. Metalloids usually conduct electricity and heat better than nonmetals, but not as good as metals, so they're kind of in the middle. And they often are used as semiconductors or even insulators. So here in this table you can see the comparison, the features between the metal silver, nonmetal sulfur, and metalloid antimony. You can see the differences. Metals usually have higher density, higher melting points. We already mentioned they're very good conductors of heat and electricity. For nonmetals, usually the density is lower, the melting point is lower, and the conductivity is pretty low, so Metalloids is kind of in the middle. So of all the elements, about 20 are essential for survival of humans. Oxygen, carbon, hydrogen, and nitrogen, just 4 elements, make up almost entirely human body, 96% of our body mass. There are some macrominerals, calcium and phosphorus found in bones, potassium chloride found in extracellular fluid, as well as sodium and magnesium, sulfur that's found. The proteins are extremely important. They are representative elements necessary for bones and teeth, muscle contraction, nerve impulses, acid-base balance, regulation of cellular metabolism. So you see that those elements are extremely important. So this illustration on the periodic table shows you the major elements in the human body highlighted by red, macrominerals highlighted by blue, and microminerals, trace elements without which we cannot survive. Without iron, we would become anemic. Without zinc, our nails will start to crumble. And there are many more features that vanadium, chromium, molybdenum, and other microminerals, they show why they are, their importance is really hard to overestimate. So our next conversation topic is about the atom. The atom, which in Greek means indivisible, is the smallest particle of an element that retains the chemical characteristics of that element. And indivisible means that it cannot be broken down by any chemical means. For example, aluminum foil consists of essentially atoms of aluminum. The first scientist who proposed a concise and continuous logical atomic theory was John Dalton, British chemist and physicist, who suggested that atoms are tiny particles of matter, and for each element, atoms are similar to each other. However, atoms of one element are different from the atoms of other elements. When atoms of 2 or more elements that are different combine, they form compounds. And during chemical reactions, atoms are rearranged to form new combinations, to form new compounds from old compounds. It's important to understand that atoms are never created or destroyed in the process of a chemical reaction. Atoms contain so-called subatomic particles of 3 types: protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons bear no charge, and they are neutral. For our future discussions, it's important to remember that charges of the same type, positive or negative, repel, and charges of the opposite type, positive and negative, attract. So the first model of an atom came from British physicist J.J. Thomson, who in his famous cathode red experiment realized that cathode rays that were emitted by cathode with electricity running through it, that those cathode rays contained negatively charged particles, and that those particles that we now call electrons had much smaller mass than the rest of the atom. So Thomson proposed a so-called plum pudding model for the atom. You can think of it as a muffin model, where protons and electrons were randomly distributed in a positively charged cloud, like plums in a pudding. Why I like the muffin analogy, it's like blueberry muffin when blueberries are randomly distributed in a muffin, like in Thomson's model of protons and electrons randomly distributed in that cloud. However, later Ernest Rutherford demonstrated that this model was incorrect. We're going to go back to this. So far, let's talk about the structure of an atom. It consists of a nucleus that contains large protons and neutrons and electrons that orbit the nucleus in a large space around it. You can see that while the diameter of an atom is about 10 to the power of -10 meters, the diameter of a nucleus is 5 orders of magnitude less, so that shows you basically the relative relationship between the size of the nucleus and the size of an atom. Atoms, the masses of the atoms can be measured in grams or kilograms, but they are so incredibly small that using those numbers make no sense. So chemists use what's called 1 atomic mass unit, AMU, or 1 Dalton, and the mass of 1 atomic mass unit is equivalent to 1/12 of the mass of the atom for the element carbon-12, the isotope of carbon, which is carbon-12. A proton is a mass of about 1. You see the exact number here. Neutron is a mass of about 1. For our intents and purposes, 1 is perfectly fine. Electron mass is incredibly small, so we can basically disregard the mass of electron and do not take it into consideration in our conversation. Here are 3 subatomic particles in an atom: positively charged proton with a mass essentially 1, neutron that has no charge, mass 1, an electron with -1 charge, and its mass is so small, as I mentioned before, we're not going to take it into consideration. So it turns out that all atoms of an element have the same number of protons, hence same atomic number. So for instance, all atoms of lithium have 3 protons. Of atoms of carbon, all atoms of carbon have 6 protons. So they all have the same atomic number. Essential atomic number is the number that's very, very specific for each element. It's the same for all atoms of an element. And it means the number of protons in an atom. So atomic number is equivocal to the number of protons in an atom. It's written above the symbol in the periodic table. You can see it right here. And elements in the periodic table are arranged according to their atomic numbers, essentially according to the number of protons in the nuclei. So every hydrogen is 1 proton, every carbon 6 protons, every atom of copper is 29 protons. Now, as we mentioned, atomic number equals protons in an atom, but what about electrons? Well, by definition, atoms are neutral. So for neutral atoms, the net charge is 0, so number of positively charged protons should be equivalent to the number of negatively charged electrons. For example, aluminum, that has 13 protons, so has 13 electrons. So overall charge of an aluminum atom is 0. Another number that characterizes different types of elements is so-called mass number. Mass number represents the number of particles altogether, protons and neutrons, in the nucleus. It's a whole number, and usually it's not written in the periodic table. So let's take a look at this 6 elements. So hydrogen has atomic number of 1 and mass number is 1, which means its nucleus contains only 1 proton and it has 1 electron. Nitrogen has atomic number of 7 but mass number of 14, which means in addition to 7 protons here, also has 7 neutrons. Since it has 7 protons, the number of electrons is also 7. Oxygen has atomic number of 8 and mass number of 16, which immediately tells us that number of protons and neutrons is the same, it's 8, and number of electrons is the same, 8. Chlorine has 17 as atomic numbers, 37 as the mass number. So number of protons in the chlorine is 17, and number of neutrons is 37 minus 17, 20. Electrons are still 17. Iron, 26 and 58, which means each atom of iron is 26 protons. The typical iron, if the mass number is 58, is going to have 32 neutrons, but still 26 electrons. And finally, for gold, 79 protons, which is the same as the atomic number, and 118 neutrons, which is mass number minus atomic number, 79 electrons. To understand why different elements have different properties, we now need to discuss the concept of the energy levels which are occupied by the electrons in an atom. So, first, let's introduce the concept of an electromagnetic radiation. Electromagnetic radiation is the form of radiation, such as light, or X-ray, or gamma rays, or radio waves. Electromagnetic radiation is comprised of the energy particles, often referred to as photons, that move as waves of energy. I know that is kind of confusing, but it is one of the concepts of the modern physics, that electromagnetic radiation is both particles and waves. The distance between the peaks of the waves is the wavelength, and the number of waves per measure of time, like per second, is the frequency. So distance and frequency are inversely correlated. Radiation that is high energy has a shorter wavelength. So basically gamma rays and X-rays have really short wavelengths. Low energy radiation, such as microwave or radio waves, they have low energy and they have longer wavelengths. So if you will heat up an element and pass the light that this element emits through a prism, the prism will split the light into distinct lights of color. This is called an atomic spectrum. Each element has its own unique atomic spectrum. So basically, if you will light up sodium versus calcium versus lithium, you're going to have a distinct set of bands. And using these atomic spectra, you can distinguish between different elements. So why these lines in the atomic spectra appear, and why do they appear differently for different elements? Turns out that the lines in the atomic spectrum are associated with the energy of electrons in the atom of a particular element, more specifically with the electrons changing their energy levels. So in an atom, each electron sits at its own energy level. Think of it as a multi-floor building, and each electron occupies a specific floor. Energy levels are assigned so-called principal quantum numbers, n and 1 and 2, and as energy of the level increases, the value of n increases. When energy level increases, these energy levels with higher principal quantum numbers, higher n, are farther away from the nucleus. Interestingly enough, electrons cannot occupy whatever energy level they want. Energy of an electron is what's called quantized. So electrons can only have very, very specific energy values, just like you cannot leave between the second and the third floor. So here you can see the electromagnetic spectrum. So this is the visible light, the light that we see, and you see that as we go to the lower frequency, higher wavelength, electromagnetic radiation, low energy, we're talking about radio, television, cell phones, and high energy radiation has very, very high frequency and short wavelengths, such as ultraviolet or X-rays or gamma rays. So here you have an illustration of electrons and the energy levels. So you see you have a couple of electrons that are occupying the first energy level, okay, and here you have 5 electrons that are occupying the second energy level. When electrons absorb energy, they move to the higher energy level right here or here. The more energy is absorbed, the higher the jump is going to be. When they move back from the higher energy level to lower, they're going to emit energy. Depending on the difference between two energy levels, the energy can become high energy or low energy. Okay? So basically, you go up a floor, you need energy to do that. But when you jump from the floor, third floor to second floor, you're going to emit energy. So we're going to talk about the electron arrangements in the periods, different periods. We're going to start with the period 1. So hydrogen has only one energy level and there's only one electron on it, while helium has also one energy level, but it has 2 electrons on it. So for instance, lithium, which is second period, and pay attention to this. So, elements in the second period have 2 energy levels, and the first energy level is fully occupied by 2 electrons, and the number of electrons on the second energy level progressively increases from 1 to 8. So essentially the number of period in which a certain element sits corresponds to the number of energy levels. All elements of the second period have 2 energy levels. All elements of the third period have 3, and so on and so forth. Here you can see the third period elements, the representative elements. So first energy level is fully occupied by 2 electrons. Second energy level is fully occupied by 8 electrons, and third energy level progressively increases the number of electrons as we move from the first group to the 8th group. Here the fourth group, here you can see that potassium, still representative element, has first, second, and third energy levels fully occupied. It has 1 electron in the fourth, and calcium, which is in the second group, has 2 electrons in the fourth. So how does it work sort of theoretically? So in theory, the maximum number of electrons on each level so far is presented here. So 8 on the second, 18 on the third, 32 on the fourth, same as for fifth. Then the 6th and 7th, the number of electrons decrease. So you can write electron arrangements distributing electrons between different energy levels. So for instance, for oxygen, first energy level has 2 electrons, and the second has 6. For phosphorus, first energy level is 2, second is 8, and the third is 5. For calcium, first is 2, second is 8, third is 8, and the fourth has 2. So these electron arrangements are really important to determine the properties of elements. Properties such as the atomic size, the energy of ionization, and the metallic character of an element. So we're going to focus on representative elements in the groups from 1A to 8A, and their chemical properties are determined by the number of so-called valence electrons. So valence electrons represent the number of electrons in the outermost energy level. For representative elements, that's important, for representative elements, the number of the group gives you the number of valence electrons. So for instance, sodium oxygen, let's say oxygen, is in the 6th A group, so it has 6 valence electrons. Calcium is in the 2nd A group, so it has 2 valence electrons. So this illustration here shows you the correlation between the group number for representative elements and the number of valence electrons. To record the number of electrons using the symbols, Lewis structures are often used. They represent valence electrons as dots on the sides of the symbol. So for instance, for aluminum, we do not picture the fully occupied 1st and 2nd energy levels. We only show 3 valence electrons. For magnesium, for instance, we can draw any of these electron-dot symbols. They all are acceptable, absolutely. Magnesium has 2 valence electrons. Okay, so we do not draw the first 2 energy levels, which are fully occupied. We're only focused on the valence electrons. So here are some examples of the Lewis structures for different elements. For instance, neon, which is a noble gas, has all 8 valence electrons. Chlorine has 7, sulfur has 6, nitrogen has 5, carbon has 4, aluminum has 3, beryllium has 2, potassium has 1. You can clearly see that these examples fully reflect the correlation between the group number and the number of valence electrons. That's basically what the group number represents. So what is atomic size? Atomic size is determined by the atomic radius, the distance between the outermost electrons and the nucleus. So the law, sort of a trend for atomic size, is that atomic size increases only for representative elements as you go from top to bottom of the periodic table. Atomic size essentially increases in the same group as you go from top of the group to the bottom. Within the period, atomic size decreases as you move from left to right. This happens because the number of protons in the nucleus increases, and these protons and corresponding electrons attract to each other much stronger, thereby reducing the size of the atom. So to kind of summarize, the size of an atom increases for representative elements from top to bottom because the number of energy levels becomes higher and higher. And atomic size, or atomic radius, changes in the period from left to right because the number of electrons and number of protons increases, and there is a stronger attraction between the electrons and the nucleus. So here you can see an illustration of what we were just talking about, that the atomic size increases as you go from top to bottom of the group, and it decreases as you go from left to right across the period. An important concept that is associated with atomic size is the ionization energy, which is the energy that's needed to remove one of the outermost valence electrons. So for instance, if you apply ionization energy, whatever it is, to sodium atom, you'll be able to snatch one electron from the sodium atom, creating a sodium ion. So it turns out that the farther the electrons are from an atom, the lower the ionization energy is. So this is why, as you move down from top to bottom of a group, the size of an atom increases, and therefore ionization energy decreases. And kind of, similar idea size and ionization energy, you can see it in the period. As you move from left to right in the period, the size of an atom decreases, therefore ionization energy increases. So now we can determine what is the metallic character of an element is. So elements are called metallic or having metallic character when they easily lose electrons. So metallic character is of course more prevalent in metals, especially in the metals on the left side of the periodic table, such as alkali or alkaline earth metals, and much less, metallic character is much less pronounced for nonmetals on the right side of the periodic table, such as chlorine, all halogens, sulfur, oxygen, selenium. Those elements do not lose electrons easy. So basically we can say that metallic character increases with the increased size of an atom, so it increases from top to bottom of a group, and it decreases as we move from left to right of the period because the size of an atom goes down and the ionization energy goes up, and these elements are much less likely to lose the electrons. So this slide gives you a summary of the trends in the periodic table. You should know them for the exam. I'm not going to review them anymore, and I hope that was more or less clear.